Okay, here we are, 3-3, day 1. All right, the last 2 days we've been talking about independent events, where if something affected the outcome of the second one, that was considered dependent to change the sample space. Today we're going to talk mutually exclusive events. Mutually exclusive events. These are events that cannot occur at the same time. They have nothing in common. So when I'm looking at two events, event A and event B, if I can be an outcome and be a part of both sets, then these two events are not mutually exclusive. So if one outcome can be in both events, then that's considered not mutually exclusive. If the two events have no overlap, that means no outcomes that can be in both at the same time, that is considered mutually exclusive. So now I'll go through some examples that may have that make sense. So example 1, I'm going to give you two events, and all you have to say is whether the two events are mutually exclusive or they're not mutually exclusive. Okay, so we're going to look at rolling a die, and event 1, we're going to be looking at rolling an even number. Event 2, we're going to be looking at rolling a number greater than 4. And I'm asking, are those two events mutually exclusive? Well, if you list all of the outcomes out, and if there's any overlap, then they're not mutually exclusive. Or you're asking, can I be an event and be in both of these at the same time? Well, evens, we're looking at 2, 4, 6. A number greater than 4 on a die, that's 5 and 6. Because 6 is a member of both of them, that's overlap, these are not mutually exclusive events, because they can happen at the same time. Okay, how about picking a card from a deck of cards? Event 1 is going to be picking a heart. Event 2 is going to be pick a face card. Well, if you think about the deck of cards in the hearts, you've got 13. You've got the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So there's 13 outcomes in that event. Face cards, remember, are all of your jacks, queens, and kings. And we've got jacks, queens, and king of hearts, jack, queen, king of diamonds, jack, queen, king of spades, and jack, queen, king of clubs. So is there overlap here? Absolutely. The jack, queen, king of hearts are counted here as face cards, and they're counted here as hearts. So these are not mutually exclusive. So you're just asking yourself, can there be at least one outcome in both of these events? If you can find something in both that's the same, they are not mutually exclusive. one last one. We're going to be looking at rolling a 1 on a die, and then rolling an even. Okay, these two events are mutually exclusive, because the 1 is just the 1, that's the only thing in that outcome for that event. This one's 2, 4, 6. No overlap, these are mutually exclusive. Oops. So, you're going to see where this mutually exclusive comes into play with today's probability question. Today we're going to introduce the word or, the probability of A happening or B happening. Okay, when you have the word or, we just finished with and we would multiply probabilities. With or, we have to add the probabilities together. So it's the probability of the first one happening added to the probability of the second one happening. But that's only true if they are mutually exclusive. Okay, because that means there's no overlap, so you're only counting the events one time. If they are not mutually exclusive, then you've got to subtract the ones that were double counted. So the probability of A happening or B happening, again, we always add, but then you got to ask yourself, was there anything that was double counted because they were not mutually exclusive? If there are, you've got to subtract the ones that were in A and B, or I call it the overlap. Book says A and B happening. I call it the overlap. So let's go through some examples. You know what I'm talking about here. So we'll roll that die again. Can you find the probability that you roll? Probability of rolling a number greater than 3 or an odd number. Or means we're going to add those two events together. So, are these mutually exclusive? Are numbers greater than 3 exclusive of the odds? No, there's going to be overlap. So, I want to find the probability that a number is greater than 3, and I'm going to add to that the probability that it's an odd, and I know there's going to be double counts here, overlap, so I'm going to subtract the overlap. So, numbers greater than 3, that's 4, 5, and 6, so there are 3 out of 6 there. Odds, 1, 3, 5, there are 3 there. Well, according to this, I'd have a 100% chance of that happening. Well, not true. I double counted, if you look at the outcomes here, I double counted the 5, so that's one number that double counted, so I got to subtract off that 1/6. So I've got a 5 out of 6 chance of rolling a number greater than 3 or an odd. So when you see or, remember, do I have to subtract off any overlap? Okay, number 3. Let's pick one card from a deck of cards. What's the probability? We'll do that one that I just had. The heart or the face card. Let's go with that one. Where are you? Right there, that part B. What's the probability that you pick out a heart or a face card? So, or tells me to add my probabilities together, but then subtract any double counts, overlap. So again, hearts, I know there are 13 hearts in the deck out of the 52 sample space, or it tells me to add. Face cards, that's Jack, Queen, King of Hearts, Diamonds, Clubs, and Spades. So that's 12. And then the ones that got counted here and here are the Jack, Queen, and King. So there's 3 cards that I double counted. So that will be, let's see, 25 minus 22 out of 52, 11 out of 26. Okay. And try one from the book that's a little bit different. I'm not going to write it all out. But it says here, number 13. A company that makes cartons finds that the probability of producing a carton with a puncture is 0.05. The probability that a carton has a smashed corner is 0.08. The probability that a carton has a puncture and a smashed corner is 0.004. So first of all, are these two events mutually exclusive, having a puncture or a smashed corner? You got to ask yourself, is it possible that one of my containers has both of them? Well, they say it is right here. It does happen. So there is overlap. So these are not mutually exclusive. So we're going to find the probability that a randomly selected carton has a puncture or has a smashed corner. So the probability that your carton has a puncture or smashed corner So anytime you see or, you think add, and do I need to subtract anything? So puncture, if I go back in the reading, that was 0.05 for a puncture, 0.08 for a smashed corner, and 0.004 that has both of them that were double counted. Because if it had both, they're counted for the smashed corner and they're counted for the smashed edge. So that's that one. Okay. And then our last one is a throwback to section 3.2. You will find these in this section also. So number 5 is going to be number 17 from the book, which has 4 parts to it, but it says, in a sample of 1,000 people, 120 are left-handed. If 2 unrelated people are selected at random from the sample, find the probability of the following. Both people are left-handed. Well, let's think about, how would you rewrite that? Would you rewrite that as an and or an or? Well, both are left-handed. That means my first person's left-handed and my second person is left-handed. So even though it's in this or section, this is an and problem. And we're going to do all of these as ands. But to get these probabilities, I believe we are not replacing these people, so these are without replacement, making this a dependent situation. So we're going to make the tree to help us out. So when I pick my first person, I am looking to see if they are left-handed. And if they're not left-handed, we're calling them right-handed. And according to the information, 120 out of 1,000 are left-handed. That means we have 1,000. How many right-handed people would be 880 out of 1,000? That would be the probabilities for picking my first person. Now I pick that person, they're off to the side. Now I pick a second person. My second person could be left-handed or right-handed off of each one of these situations. So let's go. Given that my first person is left-handed and they're off to the side, my sample space is now down to 999. So I've limited my sample space by 1. And now looking for the second left-handed person would be 119. instead of the 120. And here, my sample space is down to 999, but because my first person out was left-handed, I still have all of my right-handed people, which was 880. Down here, now I'm looking at my first person out being right-handed, so that means I'm still picking out of 999 for my second person, but all left-handed people are still in because it's a right-handed out, so I got 120. And then here, my second person being right-handed would be 879 out of 999. And now let's look at the probability questions. The tree makes it worth it if you're going to be doing several probability questions, which we are. So we're picking two people, which our tree shows. We're looking for the probability that both are left-handed. Again, in your head, you've got to turn that into left-handed and a left-handed, telling us to multiply and not add. So I just follow the branches out. 120 out of 1,000 multiplied by 119 out of 1,000. And again, I'm not going to finish that up because for notes, this is what's important. You can finish it up on homework and get the decimal place out to the thousandths place, it looks like. Okay. Second question, what's the probability that at least one of the two people is left-handed? Okay, the best way to do the at least ones is to go 1 minus the probability that I have neither left-handed. Okay, neither left-handed, what does that mean? What situation is that on this branch here? Well, neither left-handed would mean right-handed and right-handed. So it's 1 minus, now this is an and situation, so I'm going to multiply 880 over 1,000 times 879 out of 1,000. So neither left-handed means the situation I was looking for was getting a right-handed and a right-handed. Okay. Probability that neither person is left-handed. Now let's go probability of getting one of each. Well, if you look at our four outcomes here, which aren't equally likely because of the different probabilities, so I can't just say 2 out of 4, because this first one's left-handed, left-handed, this one's left and then a right, this one's right and then a left, and this one's right and right. So getting one of each, again, rewriting that, it's these two probabilities here. It's the probability of a left and then a right, or it's the probability of getting a right-handed person and then a left-handed person. So this one has ors and ands in it. So this is where the tree definitely came in handy. So the left and right would be following the branches. Get this on here. Right here. So following it out, the first left is 120 out of 1,000. And tells me to multiply. Right, 880. Or tells me to add. Probability of right, 880 out of 1,000. And is multiply. 120 out of 999. And there it is. You just calculate work from that. Okay, that's going to finish that up.